Well, it's time to discuss disorders of acid-base balance. This is supposed to be a user-friendly acid-base balance and imbalance lecture. I really enjoy teaching this lecture, especially face-to-face to my physiology students. So it is basically the same lecture I give them, and the reason why we teach them acid-base balance and imbalance disorders is because this is a very frequent occurrence in a hospital setting. Here you're seeing an equation. You are seeing a chemical reaction. You are seeing on the right side water and carbon dioxide reacting to form carbonic acid, H2CO3. And that dissociates into hydrogen and bicarbonate. It is the hydrogen that I want you to notice. That's going to be the side of our equation where, if the equation moves from right to left, we are going to be making a lot of hydrogen, and you should be thinking acidosis. If you see the equation shifting to the right, it is an effort to remove hydrogen. At the bottom of this slide, you're seeing a modified equation for pH. This is the Henderson-Hasselbalch equation. This equation addresses our body's buffer system, bicarbonate, which is shown in that equation, and it deals with CO2, which is part of how we generate bicarbonate. So through the course of this lecture, I am going to explain to you what pKa means and what this ratio of bicarbonate to carbon dioxide really means. An acid is any substance that will dissociate a hydrogen ion and then become more negatively charged. The hydrogen ion is a proton, and the electron that the hydrogen ion had stays with the original molecule. So an acid is something that will dissociate hydrogen and then take its electron away from it and then become negatively charged. When hydrogen ions accumulate in a solution, we say that the pH of that solution is dropping. A low pH number represents a high concentration of hydrogen ions. It is an inverse relationship, and I will explain why. A base is a chemical that can take hydrogen ions from the solution and bind to them. So the base is going to remove hydrogen ions from solution, and that means the pH will go up. So this base has an extra electron. It has a negative charge. It can donate that electron to hydrogen that is free in the solution and create a bond. Now those of you that have more chemistry than others, I want you to know that I do know that hydrogen ions are not free in solution. Rather, they make hydronium ions. But I am just going to say free in solution from here on out. It is just easier for me to explain a hydrogen ion instead of having to explain hydronium ions. As we move on, I want you to think of acids and bases as the two sides of Velcro. They stick together. They like to neutralize each other, and that is important to understand because if your body is in a state of acidosis, it's going to try and swing the other way and make more base to neutralize the acid. I'm going to explain how we can modify the Henderson-Hasselbalch equation I showed you into basically two entities: carbon dioxide, which is a gas of course, and bicarbonate, which is not a gas, but we still consider it as such when clinically the term arterial blood gases is used. Until I get to that modified Henderson-Hasselbalch equation, I do want to show you the traditional pH equation, and pH is the negative log of the hydrogen ion concentration, or another way of saying that is the inverse log of hydrogen ion concentration. I'm going to stick with the first way I just showed you, the negative log of the hydrogen ion concentration. If you're looking in the blue box, you will see that our pH values range from 0 to 14, at least on this screen. But I'm here to say that we can have solutions that are so concentrated with hydrogen ions that they can actually have a negative number. That would be a very, very strong acid. Solutions with a low pH have high acid content, and solutions that have a high pH value have low acid content. It's because of that inverse relationship that you're seeing here on the right side of the equation, where it says pH is the inverse log of hydrogen ion concentration. So if hydrogen ion concentration goes up, that is in the denominator, then that means pH values will go down because that is in the numerator on the other side of the equation. How do we actually calculate the log of something? What does that mean? Well, taking the log of a number that is at the base 10 is actually really easy. It's supposed to make it easier for you to multiply and divide with numbers that have exponents. Okay, so why is our body pH 7.40? Well, first of all, I think I should tell you that the amount of hydrogen ions in our body fluids has been quantified. And that number is 4 times 10 to the negative 8 moles per liter. That is how many hydrogen ions we have. If I know the hydrogen ion concentration, then I can substitute that into my pH equation, which I show here in step 3 on slide 5. If I insert the hydrogen ion concentration into that equation in step 3, I get pH equals the negative log of 4 times 10 to the negative 8. Now, with this log function, what you can do is distribute it to the numbers that are inside that bracket. When you do that, you can separate them so that you no longer have the times. You can add a plus function. I know it seems like I'm doing wizardry with the math, but trust me, it is sound. It's a function called distribution. In step 4, I am simply showing you that I am going to take the negative log of 4, and I'm going to add that to whatever I get when I take the negative log of 10 to the negative 8. In step 5, I'm doing an extra step. I'm showing that the number 4 is really another way of saying 2 times 2. Then in step 6, I am again just distributing that log function. I am going to take the negative log of 2 and add it to another negative log of 2, and then add that to the negative log of 10 to the negative 8. Now, when you take the log of something that already has the base 10, and that 10 has a superscript number, an exponent, in this case I have negative 8, when you take the log of the base 10, you simply take the exponent and bring it down. You take it out of that superscript position and put it down as if it were a regular number. That's what you're doing with the log function. When I do that, I take my negative 8 out of the superscript or exponent position, and a negative 8 times a negative value, which is right in front of that log sign, will make it positive. In step 7, you are seeing my resulting plus 8. Well, what about the log of 2? This is just a good thing to know. The log of 2 is 0.3. So you are seeing here in step 7, every place where I had the negative log of 2, that will end up being a negative 0.3, because the log of 2 is 0.3, but there is a negative sign in front of it, so that is going to have a negative value. In the end, I get 8 plus a negative 0.6. I'm hoping you're following my math here. And that equals 7.40. It is because we have 4 times 10 to the negative 8 moles per liter of hydrogen ions in our body fluids, plasma specifically, that we have a blood pH of 7.40. What if our acid levels doubled or halved? Okay, let's take double. If we go from 4 times 10 to the negative 8 to 8 times 10 to the negative 8 and use that same pH equation, we realize 8 is really another way of saying 2 times 2 times 2. In this bullet, right underneath 8 times 10 to the negative 8, I'm using the distributive property again. If I take the negative log of 2 and do it again for the next 2, and do it again for the next 2, then I am going to have 0.3 for each of those, 3 times over, right? So I'm going to have a negative 0.9. I already told you that the log of 10 to the negative 8 is going to be negative 8. there is a negative sign in front of the log function, so a negative times a negative gives me a positive. So 8 minus 0.9 is going to drop my pH down to 7.1. What if our acids were halved? Instead of 4 times 10 to the negative 8, the acid content would be 2 times 10 to the negative 8. Well, again, I can use my distributive property, and in the end, I'm going to have 8 minus 0.3, which is a pH of 7.7. This range from 7.1 to 7.7 is roughly our vital limit. We can have acids double, we can have them halved, and that is still compatible with life. But you need to hear me on this. That person at those extremes is very critically ill because we have a problem of maintaining our protein structure at those extremes. We are particularly worried about acidosis because our body is constantly producing acids. I will show you where exactly in just a moment. The accumulation of acids can actually disrupt disulfide bridges, which is a way that proteins fold and use their amino acids to link to each other. Sometimes they are called cysteine bridges because it is really a cysteine amino acid that has a sulfur group. So you get two cysteines together and their sulfur groups can interact to create a disulfide bridge. Have you ever lit the fireplace and you're turning on the gas and you're throwing in your match and you accidentally singed the hair on your arm and it smelled like burning egg? That is because you have actually allowed those disulfide bridges to break apart, and you are releasing sulfur dioxide, and that has an egg-like smell to it. So the next time you burn yourself, you are denaturing your proteins in your own skin, and you smell that egg-like smell. It's that sulfur dioxide. You're adding oxygen to those disulfide bridges in your proteins and releasing the sulfur dioxide. I'm hoping you're getting the idea that we really want to maintain our acid-base balance so that we don't denature our proteins. Now in this picture, you're seeing that the vital range is a little bit larger than what I just told you. I am using 7.1 to 7.7 because it is easy for me to remember that we can live with double the acid content and half the acid content. Then if you look critically at this slide, you're seeing that the normal range that we associate with health is 7.35 to 7.45. I'm still here to tell you that a person that has a pH of 7.35 isn't feeling well, even though this is considered normal range. Same thing with 7.45. They aren't feeling well. I'm going to discuss with you some of the manifestations that a patient will show you in acidosis or alkalosis in just a moment. Maybe you are wondering where the acids come from in our body. Acids are being ingested all the time by you in your food, and they are also being created through glycolysis and the Krebs cycle. I want you to know that as long as you are living and breathing, you are constantly generating acids as the byproduct of metabolism. The breakdown of proteins leads to acids. Anaerobic respiration of glucose, of course, yields lactic acid. Metabolism of fats still leads to organic acids and ketone bodies. Even transporting carbon dioxide as bicarbonate will lead to a release of hydrogen ions. So we are constantly bombarded with acids, and our body is trying to first create a temporary fix for that by neutralizing the acids, buffering them, until organ systems of the body, like the lungs and kidneys, can get rid of these acids. Acids, when they are synthesized, made in cells through normal metabolism, need to be removed from those cells. They need to then enter the interstitial fluid and then enter the plasma. The problem is this. When the acids are being made, the pH of the cell will drop, of course, and this can denature proteins. If the acid leaves the cell through the cell membrane and enters the interstitial fluid and then the plasma, there are proteins in these fluids too, and they could be denatured. So there needs to be some way, when these acids are made, that they can be temporarily neutralized until they can be eliminated from the body. Now, in the kidney, the kidney is going to eliminate a lot of acids through filtration and secretion, and of course, these acids end up in the urine. You don't want that urine to become so acidic that it burns all the way out. We need buffers to neutralize those acids in the nephron. We need renal tubular buffers, something in the nephron that will act as a base and neutralize these acids that are going to be excreted. The two most important tubular buffers are going to be your phosphate buffers and your ammonia buffer. You are seeing two opportunities here with the phosphate buffers. There are two forms of sodium phosphate. There is disodium hydrogen phosphate and sodium dihydrogen phosphate. The sodium dihydrogen phosphate is shown here in the red equation, and you are seeing acidosis next to it. So when a person has a lot of acid and they need to excrete it from the body, you actually can create a sodium dihydrogen phosphate where more hydrogens are being bound to the phosphate buffer and removed from the body. You can detect that in a patient's urine. If we detect more sodium dihydrogen phosphate, we know the patient is in a state of acidosis. If, however, we detect more of the disodium hydrogen phosphate type, then we know they aren't in a state of acidosis. They are probably more in the alkalotic state. Ammonia is another important renal tubular buffer. Ammonia is NH3. If you have excessive acid being secreted by the kidneys, it can bind to ammonia and create ammonium, which is NH4+. So increased sodium dihydrogen phosphate and increased ammonium in the urine would alert the physician that a patient is in a state of acidosis and is attempting to compensate for that condition by increasing the amount of acid excretion. Now, just as a side note, the ammonium in the urine mixes with chloride. That is also being excreted. This ammonium chloride creates what is called frothy urine. It is thick urine, and it does froth over when they are urinating. It is all bubbly. This is from the ammonium chloride. I have addressed tubular buffers, but what about buffering inside cells and outside cells when the acids are being made and transported in the plasma? Proteins themselves can actually be really important buffers. We have a large amount of proteins inside the cells, of course, and we have proteins that are dissolved in our body fluids, like in plasma. The most abundant protein in plasma is albumin. What you're seeing down here in the bottom equation is that hydrogen can bind with hemoglobin. This is basically reflecting that inside erythrocytes there is a large amount of hemoglobin. That is the most abundant protein inside a red blood cell. Hemoglobin has a high amount of histidine amino acids. Histidine is shown here at the end of my pointer on the screen. It can create what is called a Schiff's base. The Schiff's base is basically a histidine with its nitrogenous ring that can bind to hydrogen reversibly. Hemoglobin and other proteins can bind to hydrogen and neutralize them in their histidine residues, and then release them, or it, hydrogen, when appropriate. Let's focus with the erythrocyte. When a red blood cell is traveling through a capillary bed in a metabolically active tissue bed, there is going to be a lot of acids. The hydrogen that the cells are making can bind with histidine residues inside or on hemoglobin. Then when that red blood cell travels to the pulmonary capillary bed in the lungs, it can release the hydrogen, and it will be converted to carbon dioxide and eliminated from the body. This is what I mean by reversible. In the tissue bed, there is binding of hydrogen, and in the pulmonary capillary bed, there is release. So hemoglobin is acting like both an acid and a base. It is acting like a base in the tissue bed where it binds to hydrogen, and then in the pulmonary capillary bed, it is acting like an acid and releasing the hydrogen. There is another important buffer system besides the ones on the previous slide. Now, proteins are actually physiologically the most important buffer system our body has. But clinically, it is the bicarbonate buffer system that we are interested in. The reason is this: we can measure it. We don't really have the ability to measure how many proteins you have in your cells and in your interstitial fluid. We also really don't have a way to directly measure how many phosphate buffers you have in your kidneys or ammonia molecules. So the most important one to us clinically is the bicarbonate buffer system. It's another extracellular buffer system. It is going to work in the following way. In the picture you are seeing carbon dioxide being produced by a metabolically active tissue bed. The CO2 dissolves out of the cell into the interstitial space and then finally into the plasma of the blood. That CO2 can continue to diffuse into the red blood cell. Inside the red blood cell is a special enzyme called carbonic anhydrase. Carbonic anhydrase, being an enzyme, will lower the activation energy for the following reaction. CO2 plus water gives carbonic acid. That is shown here in step number 2. If you were to take CO2, blow into a plastic bag basically, and add water, the water and CO2 in that plastic bag would naturally react and form carbonic acid. But so few of these types of reactions would occur at normal air temperature. The carbonic anhydrase is going to help facilitate this reaction. It lowers the activation energy. Once carbonic acid is made, it will dissociate into hydrogen and bicarbonate. The bicarbonate will diffuse out of the red blood cell, and the hydrogen, do you see what is happening to it? The hydrogen inside the red blood cell, if it is not neutralized of course, is going to denature proteins. So you are seeing the hydrogen bind to a histidine residue in hemoglobin, and that histidine residue is going to make sure that the hydrogen ions are neutralized. They are going to be bound to the histidine residue so that it can't drastically change pH inside the red blood cell. Just to do it one more time, look at the bottom of this slide. You are seeing our master equation all over again, starting from the right. I have a lot of CO2, and I'm going to mix it with water and convert it to carbonic acid, thanks to carbonic anhydrase, the enzyme. Carbonic acid will quickly dissociate into hydrogen and bicarbonate. Bicarbonate can diffuse across the red blood cell membrane and be transported in the plasma, while the hydrogen ion is going to be buffered by the histidine residues in hemoglobin. When this red blood cell gets to a pulmonary capillary bed, this equation will actually reverse. I'm going to explain why in just a moment when I review Le Chatelier's principle and the isohydric principle as well. Buffering is good, but it is a temporary solution. Excess acids and bases must be eliminated from the body. Like I said, that red blood cell, when it gets to the lungs, the bicarbonate will come back into the cell, and the hydrogen will come off the histidine residue of the hemoglobin molecule, and the two of them will reform. You will notice that this equation is reversible. Hydrogen and bicarbonate will reform carbonic acid, and this will now dissociate into water and carbon dioxide. The carbon dioxide will diffuse out of the red blood cell into the plasma and into the alveolus, where obviously it can then be ventilated out. So your lungs remove your volatile acids, your carbon dioxide. But what about acids that are not gases, non-volatile acids like uric acid, creatinine, lactic acid, and other types? Well, the kidneys are going to have to be the ones to remove those types of acids. They will have ways to filter them out of the body or actively secrete them into the lumen of the nephron. Now students often say, why just the lungs and the kidneys? Don't we get rid of acids through our digestive system, through our feces, by defecating? Yes, you do. But how often do you do that in a day, much less an hour? Yet you breathe at least 15 breaths per minute, and you are producing about 2 milliliters of urine per minute. So you're actually getting rid of these acids much, much more rapidly through the renal and respiratory systems. You wouldn't want to rely on your GI tract for removing these acids. They are basically being made much too quickly, and you don't defecate that often to get rid of them before they would do serious damage. Buffering is good, but it is a temporary fix. It is a temporary solution to the problem. We need to get these acids out. Well, they are made in the tissues and they need to be transported in the blood. Obviously, the blood is going to have a very important buffer system, and that is the bicarbonate buffer system. It is the job of this buffer system to neutralize these acids and then release them so that the kidneys and lungs can remove them from the body. What is a buffer? A buffer is a substance that can resist drastic changes in pH, even when acids or bases are added to it. Our bicarbonate buffer system, let's see how it can resist changes to pH. Let's first address our equation shown here. Start from the right side. Water plus carbon dioxide, in addition to carbonic anhydrase, a very important enzyme that facilitates this reaction, will make carbonic acid. That will dissociate into hydrogen and bicarbonate. Now, remember hydrogen. I want you to think of the left side of this equation as our acid side. How can I have this equation shift to the left, and what do I mean by that? Let's say we have equal amounts of water and carbon dioxide and equal amounts of hydrogen and bicarbonate. And there is an equal amount of carbonic acid being synthesized between these two sets of molecules. Le Chatelier's principle says that when you have a system in equilibrium and you disrupt the system such that it is not in equilibrium any longer, the reactions will change to re-establish the equilibrium. The isohydric principle is basically the same thing as Le Chatelier's principle, but it applies to an acid and base and its buffer system. It says that any condition that changes the balance of one of the buffers will also lead to changes in all of the others because the buffer systems are buffering one another, shifting the hydrogen back and forth. Let's apply this. Let's say I want a shift to the left. This is shown here with the red arrows. I want to drive this equation from the CO2 and water to the hydrogen and bicarb. That is what I mean by left shift. I have two ways I can do that. I can increase the amount of CO2, and this will drive the equation to the left to synthesize more hydrogen and bicarbonate. Or, the other option is, I can drop the amount of bicarbonate that I have, and this will help drive more CO2 and water to carbonic acid, which dissociates to replenish the lost bicarbonate. We can do the same thing if we're talking about shifting to the right. Follow the blue arrows. I have two options again. If I want to go from hydrogen and bicarbonate and make more water and CO2, I have two choices. I can increase the amount of bicarbonate in this case and drive the reaction to the right, or I can decrease the amount of carbon dioxide at the very end. This will help feed more hydrogen and bicarb toward the right. So that is what we are going to see in our acid-base problems that I'm going to teach you. If we see the person shifting to the left, then the compensation for that buffer system is going to be to try and shift to the right. Again, if the problem is a left shift, the compensation will be a right shift. If the problem is a right shift, the compensation will be a left shift. Don't worry, I don't expect that to be very clear right now, but I'm going to give you some examples of that. I just want to start putting that in your ear so that you can start to mentally mull this over. Excessive acids and bases can cause pH changes. That can lead to denatured proteins, and I have addressed that already. I need you to know a few things like the back of your hand from this lecture. Believe me, this will serve you well as future nurses and physician assistants. You need to know that always, 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 normal body pH is 7.40. You need to know that when the pH gets too high, higher than normal, above 7.45, this is alkalosis, also known as alkalemia. You need to know that the normal pH is in the middle of 7.35 and 7.45, and that is 7.40. I'm going to stick to that. Acidosis can happen in two ways. The first way is the easy way for students to wrap their brain around. How can you be in a state of acidosis? Well, of course, by making too much acid. But there is another way that you can have acidosis. What if you had too little base to neutralize the acids your body was making? Didn't you hear me say that when I shift left or when I shift right, I have two choices? If we did a left shift, that means we're getting more acid. How did I do that? I said I could increase CO2 or decrease the amount of bicarbonate. The increase in CO2, that's an acid, I can cause acidosis. Bicarbonate, it's a base. I can decrease the base. So those are our two ways to get acidosis. How can I get alkalosis? That is a right shift. I can have too little acid or too much base. In red on the slide, I am pointing out the two ways we can get into acidosis or alkalosis. I will remind you, acids and bases neutralize each other, so think of them as a one-to-one relationship for the time being. How can you have acidosis? Too much acid or not enough base. How can you have alkalosis? Too much base or too little acid. So what do you need to know from this slide? A number 1, firstly, our normal pH is 7.40. B number 2, secondly, there are two ways a person can be in acidosis or alkalosis. These are very important concepts.